So let me today make a video in which I give my TED talk, which is about, does the central dogma of biology contradict the laws of physics? There's the sound coming through. So what I want to do is let me just begin by saying this. What I'm trying to do here is just to advertise my work, to give a lecture, a TED talk on the the topics that I've been studying, the scientific subjects that I've been studying in the last few years. And I didn't really want to do this as a live stream. However, sometimes it's easier to do it as a live stream because you can get feedback from the audience about if the sound is working. I was going to do it on private, you see, but then what I feared was I would give a 3-hour lecture on private and then only afterwards realize the sound wasn't working. So I'm doing this live and for an audience, because if some of you pop up in the audience, you can tell me if the sound is not working. So thank you to Gothic West and thank you, Georgina, for telling me the volume is fine. If there are any others of you in the chat, can you just put a 1 in the chat to tell me that my sound is fine? Because I want to know, I would just like to know that. I always worry that the sound is not going to be correct. And as I say, I really wanted to do this in private and then post it later on. But if you do it in private with no viewers, you're never sure if the sound is working. And if you do a 3-hour private stream and then find out the volume wasn't working, you've wasted your time. So I decided I would do it live. But what I want to say is I'm not really going to interact much with the audience. I might take some questions at the end if some people have some questions. I'm not sure it will particularly interest any of my regular viewers. Thank you, Living the Dream, for turning up and telling me that the sound is okay. I really appreciate that. So thank you very much. So I believe that the sound is okay. So with that in mind, I'm going to get on and start talking about this lecture. So does the central dogma of biology contradict the laws of physics? Well, first of all, what is the central dogma of biology? The central dogma of biology basically states that DNA creates RNA, creates proteins, or maybe I'm not saying that correctly. The central dogma of biology says that information only flows in one direction. It flows from DNA to RNA to proteins, but it doesn't flow in the other direction, meaning that the DNA can sort of influence which proteins are created, but the proteins themselves can't influence the DNA. You know, to be honest, at this point in my understanding, because I don't believe that the central dogma of biology is correct, I find it actually difficult to describe what biologists really mean when they talk about the central dogma. But I guess it's about the fact that it's about the fact that DNA creates RNA, which creates the proteins, but that the proteins cannot influence things the other way around. So the proteins, if you change the proteins in a cell, that does not change the DNA in a cell. Whereas if you change the DNA in a cell somehow, if we tinker with it, we change the DNA, we will change the proteins. But if you go to a cell and change the proteins, that won't change the DNA. That is the central dogma. That is the central dogma of biology. To repeat, if we tinker with the DNA in a cell, that will change the proteins in the cell. If we tinker with the proteins in the cell, that will not change the DNA according to the central dogma of biology. Now, I believe it was Watson and Crick who coined the term central dogma. To what extent, however, they actually believed it was a dogma is another matter altogether. And some people say they were just joking when they called it the central dogma of biology. But that said, the ultimate point is that it has been taken to be a dogma. In recent years or in recent times, it ultimately has become a dogma to believe that the proteins cannot influence the DNA, or the proteins cannot influence the RNA. It's only the DNA that can influence the proteins. It's only the DNA that can influence the RNA. So anyway, what I want to do today, let me say this. First of all, so it has been, in recent times, it has been taken to be a dogma that this is true. That notwithstanding, there is scientific research, there have been lab observations which prove that it's not true. And if you look at a book called Evolution Evolution, A View from the 21st Century by James A. Shapiro, if you look at that book, you will find documented within that book a whole series of experiments where it has been shown that the central dogma is not true, is violated. And what these research papers amount to is that they're experiments. They're documenting experiments in which people have looked at the cell under the microscope and seen that the central dogma is violated. So we know from an experimental point of view that the central dogma does not hold. So that's one thing. That's one thing. But what I want to do today is to show you that on theoretical grounds, the dogma does not make sense, or at the very least, it contradicts the laws of physics, and thus physics and biology are at loggerheads on this business. I want to show you that from purely theoretical understanding, the central dogma of biology contradicts the laws of physics. And I want to stress something to you, that what I'm about to tell you is so fundamentally easy to understand that I don't want to get bogged down in details. I want to try and tell you why this is as quickly as possible. So that's, in the first instance, that's what I'm going to try and do. I'm going to try and tell you in very simple terms, why this is obviously, why the central dogma contradicts the laws of physics in very simple terms. So let's just go for it. Let me flick on this slide. Yes. So all objects are made up of protons and electrons. So let me just go on to this slide. Here we have the DNA, here we have the RNA, here we have proteins. So here's the thing. What is the structure of DNA? What is the structure of DNA? Which clever student can tell me what the structure of DNA is? Well, here's the structure of DNA. It's made up of protons and electrons and neutrons as well, but who cares? Who cares about the neutrons? They don't matter. What is the structure of RNA? Guess what? It's made up of protons and electrons. What is the structure of proteins? What's the complex structure of proteins? It's made up of protons and electrons. So here's the point, that what the central dogma says is that the protons and electrons in the DNA affect the protons and electrons in the RNA, which in turn affect the protons and electrons in the proteins. Ergo, it must go the other way around as well, because electromagnetic interactions are always two-way. So it's ridiculously simple. It's ridiculously simple. If the biologists are claiming that the protons and the electrons are having an effect on the protons and the electrons in the RNA, which in turn are having an effect on the protons and the electrons in the protein, then the protons and the electrons in the protein must be having an effect on the protons and the electrons in the RNA, which must be having an effect on the protons and electrons in the DNA. It must be two ways. But let me try and spell this out to try and clarify it, because some people, I'm trying to tell you this as simply as possible, but maybe it needs to be explained in more depth for you to fully understand it. So let's try this again, because what do we know that DNA is? It's protons and electrons. And as I say, neutrons, who cares? Let's just forget about them. You can add them in if you want. I'm just trying to keep things simple by saying DNA is made up of protons and electrons. Now, what happens when RNA is made is that the DNA opens up. The DNA uncoils, it's in certain sections, and then it opens up. What in totality is happening to the DNA when RNA and proteins are synthesized? It's very simple. The DNA is a collection of protons and electrons, and they undergo a reconfiguration, by which I mean the spaces separating those protons and electrons, they change. So that the protons and electrons in the DNA, when the DNA uncoils and opens up, these protons and electrons undergo a reconfiguration. Now let's look at the protein. As I say, what is the protein made of? It's made of protons and electrons. And the thing is that for us as physicists, you see, a biologist will say, oh, the protein comes into existence because the amino acids are synthesized. The amino acids are synthesized, and that the amino acids, disparate amino acids from the cell are brought together and synthesized into a protein. For us as physicists, however, we don't have to take this point of view. We can basically say the protein was always there in the cell because the electrons and protons that will eventually make up the protein were always there in the cell. And it was just that originally, when you had, one amino acid here and another amino acid here at the other end of the cell, those protons and electrons were just separated by a large distance. But I mean, we don't care about that. The point is they're still there in the universe. So for us as physicists, the proteins are always there. They're always secretly there in the form of disparate amino acids that haven't been pulled together yet. So again, if we look at the proteins beforehand, when they are simply a collection of disparate amino acids, then we can say the protons and electrons in the protein have one configuration. And then when the disparate amino acids are brought together and made into protein, the protons and electrons have a different configuration. So it's incredibly simple. And the same is true for the RNA. The RNA is also synthesized, but we don't care about that because for us, no protons and electrons are created. They're already there and they're just reconfigured. So when the RNA is made, we go from having protons and electrons in one configuration, and then they change configuration and are put into another configuration. I fear that my description is overcomplicating things, and I'm not getting the point across, but what I'm saying is incredibly simple. By the way, you will have noticed that I'm rubbish at doing diagrams. Thank you to whoever made this diagram. I stole it from the internet. So thanks, for providing me with this stolen diagram. Unfortunately, I'm not great at doing them myself. But anyway, what I'm saying is, what the central dogma of biology states is that the protons and electrons in the DNA undergo a reconfiguration, which causes the protons and electrons in the RNA to undergo a reconfiguration, which causes the protons and electrons in the proteins to undergo a reconfiguration. Ergo, it must all go in the reverse order as well. It must do. That cannot be true in physics. It must also be true that if the protons and electrons in the protein undergo a reconfiguration, then this causes a reconfiguration in the protons and electrons in the RNA, which in turn causes a reconfiguration of the protons and electrons in the DNA. And just to say it again, for those of you saying, oh, but the proteins are not always there, the proteins are always there from our physics perspective, because the protons and electrons, which will ultimately go into making up the protein, they are always there, even if they're contained in disparate amino acids. And from our physics perspective, when we're just looking at protons and electrons, we can say, oh, the protein is essentially there, or the protons and electrons, which make up the protein, are there. And it's simply that the spaces between them, between these protons and electrons, are changing. So I hope I hope people understand what I mean. I fear that I'm waffling on too much and making this too complicated, but it's incredibly simple to understand. But let me say this, because some people might be saying, or some people might misunderstand what I'm saying. I'm not saying so. The central dogma says that DNA affects RNA, affects proteins. I'm then using physics to say, okay, if that's true, proteins affect RNA, affect DNA. But don't misunderstand me. I'm not saying that the effect is the same in both directions. I'm simply saying that the effect exists in both directions, because let's go back to physics. Let's think about a rock in orbit of the Earth. We know that the Earth, has a gravitational pull upon the rock. But what we also know from physics is that the rock has a gravitational pull upon the Earth. Now, that pull might be tiny because the rock is tiny. Nevertheless, it exists. And that's very important. So in physics, two gravitational bodies exert a gravitational pull on each other. But that's not to say that the effect is equal and opposite. It's just to say that the effect, if body A affects body B, then body B affects body A. Even if the effect is major in one direction and minor in the other. And again, the exact same is true in electromagnetics. If one electromagnetic object affects another electromagnetic object, then the second electromagnetic object affects the first electromagnetic object, even if it's not equal and opposite, because one of these effects might be major, the other effect might be minor. So just in case anyone is misunderstanding what I'm saying, I'm not claiming that proteins can affect DNA on a massive scale, but I'm saying that if we take what the biologists are saying, and they are saying that DNA can affect proteins, then I say proteins can affect DNA, even if it's only to a small degree. That is what I am saying. I'm not saying that the proteins, if we change the proteins, well, I'm saying that if we change the proteins, we will change the DNA. But I'm not necessarily saying that if we change the proteins, we will change the DNA in such a manner that nucleotides will start changing. Not saying that at all. I'm also not saying that if we change the proteins, we will get epigenetic changes in the DNA. Not saying that at all. I'm simply saying that if you change the proteins, there will be some noticeable difference in the DNA, meaning if we track its protons and electrons, we will see that after the change in the proteins has been made, we will get a reconfiguration of the protons and electrons in the DNA. And what could that be? Well, it could just be that if we go to the DNA, we can find an atom in which one electron has jumped up in orbit or jumped down in orbit. That would be a change. So I'm not claiming, that changes in the protein, I'm not claiming that the changes in the DNA, which occur as a product of the changes in the protein, are in any way substantial. I'm not saying nucleotides change, and I'm not saying epigenetics goes on. We don't even need to get into that. I'm just saying if we look at those protons and electrons in the DNA, they will have reconfigured after we've, tampered with the protein. So let me just take a drink of water. Thank you to everyone who's bothered to tune in. Not that I'm really looking for an audience, but if it's helpful that you people are there, because you can tell me if the audio goes rubbish. So thanks very much for putting up with this. I hope some of you are paid to keep an eye on me. So this might be one of your least interesting things to watch. But anyway, I'm going to continue with it. Let me just have a coughing fit and then take a glass of water. So let me just go back to this second slide, all objects are made up of protons and electrons. Now, I really want to make this point massive. I want to write it in big letters across the sky because it's one thing for 200 years ago for, you know, if you were a biologist 200 years ago, you might have been studying your lion. And if you were a physicist 200 years ago, you might have been studying the stars. And if you were a chemist 200 years ago, you might be, you know, you might study your stinking pot of ammonia or whatever. And it's easy to understand why these three subjects were considered to be distinct. But for the last 100 years, at least, it's probably a lot longer than that, is it? It's probably more like, I don't know, don't ask me how many years it's been. But for a long time, we've kind of known that everything is made of atoms or everything's made of protons and electrons. And therefore, because of that, we have a universal language. We have a universal language which allows us to understand all objects as being the same. Because if you're a biologist studying a lion, what you're doing is you're studying a group of protons and electrons. If you're a physicist studying the star or studying a star, what you're studying is a group of protons and electrons. And if you're a chemist studying a pot of ammonia, what you're doing is you're studying a group of protons and electrons. All of these things are the same. All of these things are the same. We have a universal language which connects one to the other. and especially, let me tell you about the example of the cell and the environment. What is the cell made up of? What's the structure of a cell? It's made up of protons and electrons. What's the environment? Like what is the composition of the environment? It's made of protons and electrons. And therefore, the idea that it is somehow difficult to understand the interactions between the cell and the environment is not true. We know that everything is protons and electrons. So the cell is protons, electrons, the environment is protons and electrons. And that tells us that is important in understanding how evolution will occur. And just to get to it, right? Because, okay, inside the cell, we have the DNA, which is made up of protons and electrons. We have the RNA, which is made up of protons and electrons. We have the proteins, which is made up of protons and electrons. And then we have the cell in general, which is made up of protons and electrons. And then we have the environment, which is made up of protons and electrons. And protons and electrons interact with each other. And so in this way, from what I've just told you, it's very clear to see how the environment interacts with the DNA. The environment is made up of protons and electrons. The DNA is made up of protons and electrons. So we can understand that both are going to affect each other at the same time. So the DNA can affect the environment, as biologists say. But at the same time, the environment must also affect the DNA. That is in all of this, I'm taking what the biologists are saying, and I'm saying, well, then if you're saying this, then it must be true the other way around. If you're saying that the DNA affects the environment, which is what you're saying, then it must be true that the environment affects the DNA. It must be true because everything is made up of protons and electrons. And again, just to be clear, I'm not saying that the environment affects the DNA as much as the DNA affects the environment, but nevertheless, I'm saying it does affect it to some extent. Let me move on. This is another one of my rubbish graphics. Let me just see how this is looking on the screen. Let me just have a look. Let me just have a look how this is. Oh, it's coming off. Okay, that's quite clear on the screen. Well, it's a shit graphic, but I'm just trying to show you. If we look at the DNA, what is the DNA? It's just a collection of pluses and minuses. What's the RNA? It's a different collection of pluses and minuses. What's the proteins? It's a different collection of pluses and minuses. And if the DNA undergoes a reconfiguration, it might, the pluses and minuses might line up like this. If the RNA undergoes a reconfiguration, the minuses and pluses might line up like this. And if the proteins undergo a reconfiguration, the pluses and minuses might, align like this. The point is that If the DNA undergoes a reconfiguration and it causes the RNA to undergo a reconfiguration, which causes the proteins to undergo a reconfiguration, then everything works in reverse order. I hope, I'm going to say it again, the point I'm making is ridiculously simple. I hope I'm not confusing you by being too verbose. Let's go on to the next slide. So here's what some of you will say. Some of you will say, yeah, but Thomas, none of this makes sense because DNA is neutral. RNA is neutral. Proteins are neutral. To which I have two things to say. First of all, I don't think DNA is neutral. Atoms are not neutral. Why is an atom not neutral? Because, ostensibly an atom has the same number of protons to the same number of electrons. So ostensibly it's neutral, but actually it can't be neutral because the protons and electrons don't occupy the same space. They don't occupy the same space. And more than that, the protons are clustered together in a center. The electrons are sort of distributed more sparse. Well, I think it's fair to say the electrons are distributed more sparsely. But that said, the ultimate point is that protons and electrons do not occupy the same space. They do not occupy the same space. And therefore, I don't think atoms are neutral. And I certainly don't think molecules are neutral. So no, I don't think the DNA is neutral. I don't think the RNA is neutral. And I don't think the proteins are neutral. If we just take the DNA, for example, and move across its body, move across its form, there will be regions of positivity and regions of negativity. There will, and it might be that, they're only very minorly positive or only very minorly negative. I'm not saying we're talking about big charges here, but what I'm saying is it all points around the DNA. I suspect that the charge is skewed either slightly positive or slightly negative. So I believe that to basically to any object, but certainly to any molecule, we can look at that molecule and we can talk about its electromagnetic profile, which is a word I've just invented, but it's just telling you the obvious, which is that it tells you about the distribution of charge around that molecule, and that in some cases it will be skewed negative, and in some cases skewed positive, even if overall the object is neutral, the molecule is neutral. That surely must be true. And it is a crux of my argument. But for those of you who don't like this, because I think there will be some people who will say, I don't buy any of this. The DNA is not an ion. The RNA is not an ion. And if you argue, okay, so maybe some of you will say that, and you will say, no, the DNA is a neutral object, the RNA is a neutral object. To which I say, can you please explain to me how it is that the mechanics of the cell work, how it is that the DNA creates RNA, which in turn creates proteins? Can you explain this to me? Can you please explain it to me in terms of the laws of physics? Because if we look at the laws of physics, there are only 4 forces available to us: gravity, electromagnetism, and then there's the nuclear force and the nuclear force. Nobody knows what these nuclear forces are. That's why I call them the nuclear force and the nuclear force. But those are the 4 forces available to us. And I don't think it's gravity which is causing the machinations of the cell. And it's not the nuclear force, and it's not the nuclear force. It's not those 3. It's not gravity, and it's not the 2 nuclear forces. So it must be electromagnetism. It must be electromagnetism. But for those of you in biology who are saying, no, I don't buy this, can you do me a favor? Can you get on the phone to the physics department and can you ask them how it is that DNA creates RNA? What are the laws of physics that are causing this to happen? I say it must be electromagnetism. But if you don't like that answer, can you please resolve this issue for me? Because I don't understand. I don't understand what is causing the machinations of the cell. Let me just come back to this image, which is the unification of science. Lots of people talk about the unification of physics. Indeed, people haven't talked about the unification of physics for an awful long time. At least 100 years. But probably a lot longer. But I will talk about the unification of science, and this comes back to the point I was making earlier, which is there is no need in the present age to make a big distinction between a lion, a pot of ammonia, and a star. All of these things are the same. A house is made up of protons and electrons. So is a car. So is a cat. So is a tree. So is a can of Coke. So is urine. So a lot of things. So everything is made up of protons and electrons, and we don't need to make such big distinctions between the sciences at this stage. And in my theory that I've been working on for the last 6 years, it could be described as being an attempt to unify science. Let me come to this point. So I have shouted myself hoarse, saying that the central dogma of biology contradicts the laws of physics. I've shouted myself hoarse trying to tell that to you. But here is another big shibboleth of the neo-Darwinian paradigm. The neo-Darwinian paradigm claims that random variations are what leads to different phenotypes, different cell modifications, organism modifications. They say that random variations lead to this diversity in the animal kingdom. But of course, for us as physicists, nothing is random. If the entire universe is made up of protons and electrons, they're not going to interact with each other in a random way. So again, this is a second example, a second distinct example. This is a second distinct example where modern biology is at odds with modern physics. And in this side, I really feel like the physicists are correct. I think the issue with randomness, by the way, I think randomness is a word which often has different connotations, because oftentimes when people christen something as being random, when they christen a phenomena as being random, what they're really saying is it's complex, or it's complicated. It's difficult to ascribe a pattern. But in time, once someone has said, "Oh, this is random," I think the connotation of the word random then somehow changes to meaning it's a lottery. It can't be predicted, and those are two different things. To say that something can't be predicted is different to saying something is difficult to predict. And so I believe this is one of the things about the use of the word random, which is that it has different connotations. So often people use it to say, oh, those patterns are complex and difficult, very difficult to predict, so ergo they are random, which is not the same as saying those patterns cannot be predicted and it's all a lottery, and therefore they are random in that sense. So that's one minor issue about the word random. But I will repeat, the most important thing is that how can modern neo-Darwinism claim that genetic variations are random when the laws of physics are not random? The laws of physics are not random. Nucleotides in DNA are made up of protons and electrons. They are governed by the laws of physics or the laws of electromagnetics. Therefore, they cannot just randomly change. But I've tried to explain what I'm talking about. In terms of very concrete ideas about the fact that stripped bare of all their chemical complexity, every object in a cell is made up of protons and electrons. I've tried to tell you this, but let me try and tell you in a different way why you as a molecular biologist should really take to heart what I am saying. And that is because anyone who knows anything about molecular biology, anyone who has studied the cell in depth, anyone who has read a book like, Molecular Biology of the Cell, I think that's the name. I'm talking about that huge blue book, which is, it's about 1,000+ pages long. Anyone who has ever studied molecular biology of the cell will know that the cell is a ridiculously high precision factory. It is a ridiculously high precision factory. So, for example, let's suppose there is suddenly somewhere in the cell, there is a 0.00001% increase in the concentration of ammonia hydroxide peroxide dioxide, or whatever it's called. Then what happens is the cell reacts. The cell reacts in order to reduce this level of ammonia hydroxide peroxide dioxide down to what it originally was. And there is a whole team of organelles which suddenly arrive on the scene, like firefighters putting out a blaze. They arrive on the scene to reduce the levels of sodium hydroxide peroxide. And then there's another group of organelles who arrive on the scene to oversee this project. And then there's another group of organelles who arrive on the scene to oversee the overseers, to check the checkers. And then there's another group of organelles arrive on the scene to check that the checkers are checking the checkers correctly. It's unbelievably complicated. It's ridiculously sophisticated. It's ridiculous. And all because in one tiny area of the cell, the levels of sodium hydroxide, peroxide, dioxide, blah, blah, bloxide, they increased by 0.0000001%. It's a ridiculous level of sensitivity. It is an absolutely ridiculous level of sensitivity. Nevertheless, the cell is a highly reactive entity, which will always, if the environment changes, if there is a tiny influx of chemicals into the cell, which is not what it usually expects, it will react and it will take measures and steps. And my God, it's so sophisticated and coordinated. Everybody who has studied molecular biology of the cell, or who has studied cell biology, knows this is to be true. So with that in mind, can you now see how ridiculous it is to say that changes in the environment, which cause changes in the cell, have no effect whatsoever on the DNA? As if the DNA just stands in the middle of the cell, totally impervious to everything that's going on around it. This can't be true. It can't be true. You cannot pretend, because the DNA is made of protons and electrons, so it is not outside. It is not somehow removed from the universe. It is not somehow removed from the, being acted upon by the laws of physics. It is, you cannot have this special pleading where you say that the cell is this highly reactive entity, but the DNA never changes and nothing can basically change it. You can't have this special pleading. And of course, molecular biologists will say that oftentimes when the cell is disrupted somehow or the environment changes, the DNA does come into action. For example, the DNA uncoils and then it opens up and it synthesizes RNA. That's a classic example of the DNA reacting to to circumstances in the cell. And I say, for me as a physicist, what I notice when the DNA uncoils or when it opens up, then I say, because the DNA is just protons and electrons, I notice that those protons and electrons are being reconfigured. So that is a change for me. But the point I'm trying to say is you cannot draw this arbitrary line around the DNA and say, that is never affected, mate. It's never affected. It's never affected, mate, despite the fact that everything else in the cell is highly reactive to the environment. No, you cannot do this. You cannot draw an arbitrary line around the DNA. Now, it's probably true, and this is probably where perhaps the misunderstanding comes from, that the DNA is the most impervious entity or object within the cell. It is the least reactive. The DNA only reacts in extreme circumstances, and it reacts the less. I think that's probably true, and I think that's probably what has maybe been a factor in convincing people that the DNA is immune from change. But there is no way that it is immune from change, because if it's made up of protons and electrons, it is part of the same electromagnetic universe as everything else in the cell. Then you can't just exempt it from the law of physics and say, draw an arbitrary line around the DNA and say it doesn't change. And by the way, look, as I say, a contradiction, I think, that biologists will engage in is that they will say the DNA will open up. They will say it will uncoil. And as I say, for me as a physicist, that is a change in the DNA. But also, did I mention this before? It might be that electrons in the DNA jump up to different orbits. So there might be an atom in the DNA in which the electron has jumped up in orbit or jumped down in orbit. So it's very difficult, without going into changes in nucleotides. It's also possible that the DNA changes because it's, various electrons in various atoms in the DNA change orbits. That would be one classic way in which DNA could be changing. Thank you to those in the chat who are keeping me company. So thank you, Natman Prime. Thank you, Udwin. Thank you, Miradi80s. By the way, I should just explain, this is not really, I really wanted this to be a private stream that I would publish later, because I just want to get on and deliver my lecture. And I don't really want to be, dealing with the audience. But that said, if I did it that way and there's sound problems, I wouldn't have anyone to inform me. So I want to thank you all. Thank you, Joe. Thank you, Ride Forever. Thank you, Raspberry Treacle. And thank you, Living the Dream in Gothic Western. Thank you all for turning up and keeping me company, because if the audio if there is a problem, if there is a technical problem, I'll need the feedback. So thank you very much, guys, for tuning in. Let me just take a sip of water. So I do believe the fact that biologists know that the cell is a high precision factory, and yet, with all these organelles which react like hell, which are highly sensitive, you cannot believe that and at the same time believe that the DNA is immune to change. That is a big contradiction, I believe. Let me just say one final thing. Because some of you, in what I've said, I've made the claim that it is the protons and the electrons in the DNA which affect the protons and electrons in the RNA, which affect the protons and electrons in the proteins. And of course, one thing you will know if you know your biology is that the DNA and the RNA are often separated by big distances, and the RNA and the proteins are often separated by big distances. And so one question which struck me when I was doing this all is if the protons and electrons can affect the protons and electrons in the RNA and the proteins, which are miles away, why can the protons and the electrons in the DNA not affect protons and electrons in the surrounding DNA, which are much closer? So let me just try and make the point. I wish I had better I wish I had some fucking diagrams for this. But what I'm saying is, if you just look at, let me just remove this for a second. If you look at my hands and we imagine that they're two sides of the DNA molecule, what I'm saying is, it is the protons and electrons in this section of the DNA strand can have an effect on very distant protons and electrons in the RNA or in the proteins. But you then might ask the question, why is it that the protons and electrons in a little bit of the strand cannot affect the DNA above that section and the protons and electrons in the DNA below that section? Maybe I'm not making this clear. Yeah, but I'm hoping I've got clever students in the class. And so this, because what I'm saying is, if I'm saying that all of the reason the DNA creates the RNA, creates the proteins, all comes down to protons and electrons acting on other protons and electrons, why is it that those protons and the electrons in the DNA are not influencing very close protons and electrons in other parts of the DNA? Because typically what happens in the DNA is that a section of it opens up and gets active, while the neighboring sections are fast asleep and are inactive. And so one thing you might ask about my thesis is, why is it that the protons and electrons in the active part of the DNA are not having an effect on the protons and electrons in the neighboring DNA? Because the neighboring DNA is very, very close. To which I will say two things. First of all, because it's because of electromagnetism, and the inactive parts of the DNA are essentially in a state of electromagnetic neutrality, if I can call it that. And that's why they're not affected, even though they're very close. They're very close to the active DNA, but because they're neutral, which corresponds to them being closed, they're unaffected. And that is why the protons and electrons in the active part of the DNA do have an effect on distant protons and electrons, but don't have an effect on neighboring protons and electrons. Does that make sense? I hope it does. But that said, some of you might not like that explanation. And I was very confounded by all of this. When I first got into it. And as I say, in some ways, I don't like that explanation. Well, maybe I do actually. But there was at least a time when I didn't like that explanation and was confounded and thought this was a hole in my theory. And indeed, some of you will say, this is a hole in your theory. To which I say again, in that case, how do you explain all of this? Because all I'm trying to do here is to honestly explain why DNA can create RNA and create proteins. And if you don't like my explanation, that is fine. And I can see there are some potential holes in it. But in that case, I ask you, what is the fundamental law of physics which is causing the DNA to create the RNA and to create proteins? Because that is a question which must be answered. Anyway. Let me now move on to part 2. And all I'm going to do in this second part is to try and explain to you in more detail what I've been saying in the first part, which has just gone by. Now, I will repeat again I think that the argument I'm making is fundamentally simple, And that is why, in some ways, I abhor a more detailed explanation. However, those of you who, understand in great detail the mechanics of the cell, first of all, you will probably want a more detailed explanation. And also, I do as well, because I really want to understand this, properly and thoroughly and at a minute scale. And so that's what we're going to try to do now, or we're going to go more in that direction. There's limits to how much I can present in this thesis, in this lecture, this YouTube lecture. But what I'm saying is, although I'm going to give you a more detailed explanation, please don't forget that what I'm trying to tell you is ridiculously simple, and that the arguments that I gave you in the first 5 or 10 minutes are really the crux of everything that I'm saying. Now, we might get bogged down in some technical matters, or it might seem that way. Some of you might get bored stiff by what I'm going to say. And therefore, throughout this part, what I want you to remember is that we are trying to answer the following question. The following interesting question is, which is, how do I change the DNA of my ear? How do I change the DNA of my ear? Let me show you how I think I can do it. So here's how I change the DNA of my ear. I'm going to hold my earlobe. I'm going to pull down on it. Done. I've just changed the DNA in my ear. There you go. It's done. It's dusted. There you go. That's my claim. That's my claim, that if you just pull on your earlobe, you change the DNA in your ear. It's as simple as that. So that's my claim. And I'm going to try and justify it to you in this second part. And if we start to get, bogged down in details, and you start to wonder, what's the purpose of life? I want to shoot myself. Keep this question in mind, this fun question in mind, and we're going to try and get back to it. So let me now say something. About some important things which go on in the cell, which are not given a great explanation by biologists. Now, if you read Molecular Biology of the Cell, what is it about? I think it is about a description of what goes on in the cell. It is about an observation of what goes on in the cell. Indeed, books like Molecular Biology of the Cell are composed basically of, numerous research experiments in which the cell was observed under the microscope, and everything that goes on in the cell was basically jotted down in much the same way that astronomers once, or do study the stars with their telescopes. In this same way, biologists study what's going on in the cell under their microscopes, and they make observations. And a book like Molecular Biology of the Cell is a book of observations. It's a book of descriptions of what goes on in the cell. However, for me as a physicist, I want to know why. I want to know the why. And just to be clear, this is not a criticism of molecular biology of the cell, or of molecular biologists. Their job, because at one time, let's just be clear, nobody knew about the cell going back 100 years or so. No one knew about the cell. No one used microscopes. And then all of this stuff took off. And now we know a ridiculous amount of information about the cell. And so all of this needs to be recorded. But also, I believe there does come a point where you might want to ask the question, why? Why does any of this happen? I want to know why. I want to know why this happens. And so that is my fundamental drive in this scientific thesis I've been working on. So here we have a situation, if you look on the screen, we have a situation where we have a catalyst, and we have two chemicals, A and B, and they're coming to the active site of the catalyst. and they're going to be married, I say. They're going to be unionized. We're going to make a product called AB, and the catalyst has a central role in all of this. And if you know anything about the molecular biology of the cell, you will have seen this process occur 100 times. But here's my question. Why does it happen? Why? What is driving chemicals A and B to go to the active site of the catalyst and to join in holy matrimony? What is causing that? And again, it comes back to it. Which law of physics is involved here? Is it gravity? No. Is it the nuclear force? No. Is it the nuclear force? No. So it must be electromagnetism. So it must be that the electromagnetic profile of A is attracted to the electromagnetic profile of half of the active site of the catalyst. And it must be that the active, the electromagnetic profile of B is attracted to another half of the active site of the catalyst. So it must be, you know, if I just want to give you a cheap example, it must be that A is, let's say, negatively charged at one end, and that the active site of the catalyst is positively charged. It, you know, so that there's a plus minus attraction there. It must be something of that description. Now, I've never heard anyone say this. I've never heard anyone say this. But that's surely what must be what's going on. That's surely what must be going on. And if it's not, if you're deriding me and laughing and saying that's not what's going on, then what is going on? And by the way, because look, one thing which biologists and chemists often talk about is lock and key, whereby the shape of A and B is such that they fit into the active site of the catalyst like a lock and key coming together, which is a good way of understanding things. But I think the electromagnetic paradigm is just a little bit more helpful, because that not only explains why A and B fit into the active site of the catalyst, it also explains why they get drawn over to the catalyst in the first place. So I think that what I'm saying is making sense, but no one ever says this. Let me just come to electromagnetic profile. This is a term that I've just made up, but I feel like in all of this, you know, some language is missing, some concepts are missing. What is the electromagnetic profile of an object or of a molecule? It's simply the distribution of charge across that object or across that molecule. So here I've got two electromagnetic objects. One has got a string of pluses, then a string of minuses. But by the way, this again, my rubbish diagram, my rubbish ability to make diagrams is coming up here, because some of these pluses will be big pluses and others will be minor pluses. But I couldn't show that in a diagram because I'm fucking retarded when it comes to making diagrams. But the point that I'm trying to make is that every object, including every molecule, surely has something which we could call an electromagnetic profile. And you see here from these two objects that I've got, these two rectangles, you will see that one of them has an electromagnetic profile and the other has the opposite electromagnetic profile. So I do think we need, you know, well, I think it would be helpful to talk about electromagnetic profiles and to then talk about an opposing or the opposite electromagnetic profile, or the attractive electromagnetic profile. What I mean is, you know, we can say that an object A has an electromagnetic profile. We then might say there is another object which has the inverse electromagnetic profile to object A. And thus, if you put them together, they sort of form a lock and key. They connect together, they join together, they neutralize each other. I think these concepts would be helpful. I do think that. But anyway, so I hope I've given you some I've said something about A and B being drawn to the catalyst, which makes sense in terms of electromagnetics. I'm saying that if you look at the electromagnetic profile of A, it is going to be attracted to the electromagnetic profile of the active site of the catalyst, and that the electromagnetic profile of B will be attracted to the electromagnetic profile of the active site of the catalyst. But anyway, let's go on. Let me just say, before we go any further, that it is helpful to pretend that DNA creates RNA catalysts, and that these then, and just to forget about proteins, because in molecular biology of the cell, DNA creates RNA, creates proteins, but it's been very useful for me in my thesis, and it will be very useful for you in your thinking if you just pretend for a moment that DNA creates RNA, and that these RNAs become catalysts and, essentially do the jobs that we know that proteins do. I think this is a very important simplification of what goes on in the cell, which allows you to grasp the key underlying concepts, and then later on, you can just make the extension to proteins. Really. So this has been helpful to me, and I would advise all of you to oftentimes forget about proteins and just pretend for a moment that DNA creates the RNA, which then forms, the proteins forms the catalysts in and of themselves. That's a very helpful thing, and I'm going to do that here, is what I'm saying. So, I'm going to do that here. So bear that in mind. So here's the question then: what causes DNA to create RNA catalysts? Forget proteins exist for a moment. What causes DNA to create RNA catalysts? Now, again, if you read molecular biology of the cell, you will find that when A and B come to the cell, let's just go back to this, you will find that when A and B come to the cell and they do not find that there are any catalysts available, for some unknown reason, the DNA opens up and it starts creating said RNA catalysts. So this is one of the most amazing reactive abilities of the cell, that if A and B, the chemicals A and B, come to the cell, especially in large numbers, and they do not find catalysts that they need, or they do not find sufficient catalysts that they need, the DNA opens up and makes said catalysts. Incredible business. But the question is why? Because again, as a physicist, I want to know why this is occurring. And I'll show you my explanation, and it's ridiculously simple. But the thing is, I'll show you my explanation, and it's ridiculously simple, and which makes me think somebody must have already thought about this before. But I can be forgiven for thinking that no one's ever thought about this, because if someone has thought about this, the information is not readily available. But anyway, let me show you. So what causes DNA to create RNA catalysts? Hang on. Well, okay, which slide? Let me just use this one. Look, here's the point. Here's the point that I want to make. If A and B, we know that A and B are electromagnetically attracted to the active site of the catalyst. But we know as well that this catalyst, which is an RNA catalyst, we know that that is embedded in the DNA, because all RNA catalysts are secretly embedded in the DNA. So if A and B are attracted to the RNA catalyst, they are going to be attracted to one side of the DNA. There will be a certain, we know that somewhere on the DNA, there is a section which creates this RNA catalyst. And at precisely that section, we will find in the DNA this RNA catalyst in disguise. So if A and B are attracted to the RNA catalyst, they must also be attracted to one side of the DNA. And this is unbelievably simple, what I'm saying. And the point is that if A and B arrive in the cell and they do not find a catalyst, instead of being attracted to these catalysts, which are not here, they will be attracted over to the equivalent part of the DNA. This, again, here I feel like we need better nomenclature, better concepts, because what I'm saying, which is that I'm saying that every RNA catalyst in the cell is secretly embedded in the DNA. And if you must know what I'm talking about. You must know what I'm talking about. That every RNA catalyst in the cell is embedded in the DNA. We know this. So the point is, let me just put the hands on screen again. The point is, if this is the DNA, right? The DNA is originally closed. And let's suppose that this side of the DNA is the RNA catalyst in disguise. Then when A and B come into the cell and they find that there aren't any catalysts available, then instead they'll be attracted over to one side of the DNA, this side of the DNA, which is the RNA catalyst in disguise. And when they get there, well, let me say, so when the DNA is shut, it's shut, I believe, because this side is electromagnetically attracted to this side. And so they form a happy union. They are in love. And, I will use the love metaphor here. And what I really mean by that is electromagnetically attracted. So the two sides of the DNA, when they are closed tight together, are electromagnetically attracted to each other, and they are locked up like this. Now A and B enter the cell, and they don't find the catalyst they were looking for. So instead, they come and pester this side of the DNA, which is secretly their catalyst in disguise. So they come to this side of the DNA, and A and B basically demand that this side of the DNA start an affair with them. So what this causes is the DNA opens up. And A and B rush into this side of the DNA and start pestering it and saying, come on, we love you, come on. Meanwhile, this side of the DNA grows lonely. By which I mean it's got an electromagnetic profile here which needs to be neutralized. So this side of the DNA has grown lonely. And so nucleotides, which maybe are, which are floating about and which are in need of falling in love as well, these nucleotides come to this side of the DNA. And in this way, an RNA catalyst or an RNA string is synthesized here. So to repeat, originally, the two DNA strands are together and in love. Then they are forced apart because this side is pestered by A and B, the chemicals, who also want it. And then this side feels lonely and so attracts nucleotides to it. Then these nucleotides form into an RNA string. And the final irony is that these two sides get back together with each other, and the RNA string created runs off with A and B. And that's exactly what A and B wanted, because A and B wanted this RNA string, which is their RNA catalyst in disguise. So does that make sense? Again, I feel I'm trying to explain something which is incredibly simple. Maybe it would help if I had better diagrams. But to repeat, the two sides of the DNA are electromagnetically attracted to each other. A and B turn up in the cell. They don't find their catalyst, so they're very unhappy. But because this side of the DNA is their catalyst in disguise, they come to it and they say, come on, start an affair with us. And so this side of the DNA starts an affair with A and B, whilst this side of the DNA is left alone and forlorn, and so attracts equally forlorn nucleotides to it. And so on this side, an RNA string forms. And when it has, A and B decide to run off with the RNA string, and these two sides of the DNA say, oh, let's get back together. You had a fling, this one had a fling and this one had a fling. The two sides have a fling with different molecules. This one has a fling with A and B. This one has a fling with some nucleotides. But eventually they get back together. And they get happily married, and they say, look, we should never have had an affair. Let's get back together. Meanwhile, A and B have run off with the RNA string, which was synthesized, and that RNA string is really the RNA catalyst that they wanted all along. That's how I think it must work. But I will say, so much in all of this is keeping track of electromagnetic profiles. Because, to go back to it, if we know that the active site of A and B if we know that the electromagnetic profile of A and the electromagnetic profile of B is attracted to the active site of the catalyst, then we also know that they're attracted to a certain section of the DNA, which is the catalyst in disguise. And the other thing we know is that the two sides of the DNA are electromagnetically attracted to each other. So we know that the two sides of the DNA, because they form such a strong bond, are highly electromagnetically attracted to each other. And so by keeping track of electromagnetic profiles, it allows us to deduce the reasons why it is that if A and B come into the cell and do not find their RNA catalyst present, the DNA will open up and start generating RNA catalysts. The very ones that A and B require. That must surely be how it works. And I don't think it's complicated. I really don't. It's simply a case of tracking electromagnetic profiles. And in the first place, having the concept of an electromagnetic profile and understanding things like if two sides of the DNA are attracted to, are bound together very tightly, it must be because they are electromagnetically attracted to each other. So, but the thing is, I think that's quite simple. But again, I've never come across anyone talking about this. Because as I say, an awful lot of biology is about descriptions of what is going on. It is about descriptions of what is going on. It is not about the mechanisms which cause these things to happen. But I think that's what it must be. Where to next? Let me just get another sip of water. Hang on. So I'm sorry to break off there, but I'd run out of water and my voice is going quite badly. Let us just continue then. So where am I going with all of this? What is next? So what causes DNA to create RNA catalysts? I think we just talked about that. Okay, so let me just come to this then, because in what I just talked about, I talked about why DNA would create RNA catalysts. And some of you will be saying, that's great, I understand it, but in the real cell, in the real adult world, it is not just a case that we need to create RNA catalysts or RNA strings. They then have to go on to create the protein catalysts. But I'll show you why we've understood the fundamental argument. Because look, if A and B are attracted to the active site of a catalyst, and that catalyst is a protein, then it must be that they are not attracted to the RNA string or the RNA catalyst that created said protein. So if you have an RNA string or a bit of RNA. I'm calling it an RNA string, but it's a bit of RNA, and that creates a protein. Then it must be that there is an electromagnetic attraction between that RNA and between that protein. So if A and B are attracted to the active site of the protein catalyst, they are not attracted. In fact, they are repulsed by the RNA that created said protein. But if they're repulsed by that string of RNA, then they are attracted to the opposite of that RNA, if that makes sense. This is where we really need some language to help us out. The point is that every bit of RNA has an opposing bit of RNA which it is attracted to, which if it comes together, like forms a section of DNA, right? So what I'm saying is if A and B are attracted to the protein, they're not attracted to the RNA that made the protein, but they are attracted to the RNA, which is the opposite side of the RNA which created the protein. Oh, you know what? I really fucking despair that this is so complicated to say. But what in all of this, if A and B are attracted to the protein, then it's also true that there will be a certain section of the DNA which A and B will be attracted to. So if A and B are attracted to the protein, there is a certain section of the DNA which A and B will be attracted to. And when that bit of DNA comes apart, let me again do the hands. Okay, so what I'm saying is A and B will be attracted to a bit of DNA. And if they're attracted to this side, then the opposite side is secretly the RNA catalyst which created the protein. That is true. Just follow the electromagnetic profiles through. If you follow the electromagnetic profiles through, you'll see that what I'm saying is true. So whereas when we had the case of the RNA catalysts, A and B were attracted to this side of the DNA, which was the RNA catalyst in disguise. When we are dealing with the case of protein catalysts, A and B are in fact attracted to the other side. They're attracted to the other side, which is, the opposite of the RNA string. Oh, but the point is, it doesn't matter. Everyone gets what they want. I'm annoyed by this, but those of you who've got brains to think will understand what I'm saying, which is it's about tracking electromagnetic profiles. It's about tracking electromagnetic profiles. And if A and B are attracted to the protein and the protein was created by an RNA string, then A and B are not attracted or repulsed by that RNA string. But then they then must be attracted to the opposite of that RNA string. Fuck off. I really can't be bothered to try and explain this anymore. It's very fucking simple. It's very fucking annoying to explain, but it's all about tracing electromagnetic profiles. Because again, if you have a bit of RNA which creates a protein, then the electromagnetic profile of the RNA must be attracted to the electromagnetic profile of the protein. So the upshot of all of this is that if A and B are attracted to the protein catalyst, there is a side of the DNA they are also attracted to. That is clear, I think. So in other words, everything I've said applies for the real world of the cell, where we don't have RNA catalysts, but we actually have protein catalysts. Okay, so let me just come to this. I'm getting towards the point where I'll show you why pulling on your earlobe will cause the DNA in your ear to change, even if it's not profoundly, but it will cause a change. Look at this diagram I've got here. So I want you to imagine that one day chemical A turns up, but it's been slightly modified. And I've demonstrated that here. I've drawn it here as if A has a spike on it. I've drawn it here as if A has a spike on it. Now, what I want to try and suggest or conjecture here is that if A and B turn up to this catalyst and now A has slightly changed shape, I want to conjecture or suggest that that what A does with its new changed shape is that it bullies the catalyst into also changing shape. I want to conjecture that when A's shape is modified, then when it comes to the catalyst, it bullies the catalyst into also changing shape. To which I already hear some of you say, when have scientists ever observed this? I don't know that scientists have observed this. I'm talking about the situation in which chemicals are going to change the shape of their catalyst. And I don't know that that's ever been observed. And I don't know that that is really a thing. But if you just bear with me, I think you might understand why I'm thinking along these lines. So what this idea is about is that if A changes shape slightly, then when it comes to the active site of the catalyst, it will bully it. It will bully it into also changing shape. Look, if you think of the catalyst as being made of plasticine, then when this A arrives, it might leave a poke in the hole of the plasticine, and so the plasticine will change shape. That's the idea that I want you to consider here. I'm not saying that. Well, some of you might say this doesn't happen in reality. Okay, fine, but I just want you to go with this thought experiment for a moment. So, yes, okay. So here's yet another thing. Here's yet another thing which we need to talk about, because if biologists, when biologists talk about DNA, what will they say? They will say, oh, there's 4 bases: adenine, thymine, guanine, cytosine, A, T, C, and G. There's four bases: A, T, C, and G, and A always pairs with T, and C always pairs with G. And you will be told this, and this is always what you're told, and that is what you're told. And again, for someone like me, I want to know why. Like, what's really going on here? What's really, really going on here? So why is it that A and T form a pair? Why is it that C and G form a pair? But again, it must be because they are electromagnetically attracted to each other. That must be it. So if A and T come together, it must be because they are electromagnetically attracted to each other. Their electromagnetic profiles complement each other. They have opposing or opposite or attractive electromagnetic profiles. And if it is also true that A and C do not come together, if it's also true that A and C, for example, do not come together, that must be because they are electromagnetically repulsing each other. They're repulsing each other electromagnetically, so they stay apart. So this is yet another thing in molecular biology, which never really is explained properly, but which is you sort of infer, well, it must be all to do with electromagnetic bonds and complementary electromagnetic profiles or repulsive electromagnetic profiles. That explains why A and T come together. That explains why C and G come together. So that's that. So what about this? What is this a diagram of? This is an RNA catalyst, or it's a bit of RNA, and it's, well, when you think about RNA being formed, when RNA is formed by the DNA, I like to think of it as a string. I mean, whether it is in reality, I don't know, but I like to think of it as a string. But once that RNA string is made, it then folds up. It folds up into a complex 3-dimensional shape. Now, what determines the shape of that RNA catalyst? Well, it is the arrangement of A's, C's, T's, and G's. So, you know, as we said previously on the previous slide, A is attracted to T, C is attracted to G, and by the same token, A and C repulse each other. A and G repulse each other. T and A repulse each T and G repulse each other. T and C repulse each other. So the point is that when the RNA string takes on a shape, it does so according to whether there are electromagnetic attractions between adjacent nucleotides, or whether there are electromagnetic repulsions between adjacent nucleotides. Let me again just try and show you with my hands. What I'm saying is, you can imagine that this is the string, right? So just it's you know, from one finger end to the other, right? So if you have a C here, and then you have a G on this side, because C and G attract each other, that causes the string to close like this. On the other hand, suppose we have a C here, but an A here. Then the fact that C and A are repulsive causes the string to open like this. So there are a whole series, you know, that you have this string, this RNA string of A's, C's, G's, T's, and depending on where the A's and the C's and the G's and the T's are placed, it causes the string either to sort of fold towards itself or to fold away from itself. And what this leads to ultimately is a complex shape being formed. It leads to the RNA catalyst forming a very complex shape. So what? So what, you might say. I'm coming to an interesting bit, so hang on. Let me just see. So the point is, what is the point? If we go back to this, right? So this is, I'm talking about, we've got an RNA catalyst here. We've got A, which is you know, which is slightly changed shape, and it's got this spike on. And the point is, it's my idea is that the modified A or the modified chemical A is going to change the shape of the catalyst. So if we just come back, if we just come back to this RNA catalyst, right? Imagine just imagine you've got a hammer and you're trying to change the shape of this RNA catalyst, right? So you try to change the shape of this catalyst. You know, you might bang on a certain part of it, bang, 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 and you demand that this RNA catalyst change its shape. What is going to happen? Because it seems obvious enough to me that what will happen is, if you take this RNA catalyst and you demand that it take on a new shape, then at a certain point, an inappropriate nucleotide may drop out and be replaced by an appropriate nucleotide. Do you understand what I'm saying? If you try and change the shape of an RNA catalyst, I think what will ultimately happen is, and one nucleotide will pop out, it will be replaced by a different nucleotide, and this different nucleotide which pops in will help maintain the shape that you are trying to make. So you're taking this catalyst and you're trying to bend it or shape it into a new shape. And I'm saying that if you do that persistently enough, then one of the nucleotides will pop out and be replaced by a different nucleotide, which will help maintain which will help maintain the shape of the protein that you, of the catalyst that you are demanding. Let me just have a drink of water. Now, why does that happen? It's ultimately because of electromagnetic attraction. And again, what I'm saying, I think is really intuitively obvious, but I may be failing to describe it properly. But it makes sense to me that if you have this big catalyst, which has a specific shape, and then you're trying to just modify the shape in a certain way, it then makes sense to me that one nucleotide will drop out and it will be replaced by a better nucleotide, a different nucleotide, which will help to achieve the shape that is being demanded. And if you think about it all in terms of electromagnetics, it makes sense that it is like this. Because, to go back to it, I mean, let's suppose, so this is A, which, as I say, is changed, right? So let's just imagine, instead of A having this spike on it, it's actually got a massive negative charge on its front. So it's got a massive negative charge on its front. So it goes to the catalyst with this massive negative charge on its front. That's going to have an effect on the catalyst. It's going to make the part of the active site of the catalyst will become positively charged because this A has a negative charge on it. So the fact that A has a negative charge on it and it's coming over to the active site of the catalyst will cause the active site of the catalyst to become very positively charged. And if you think about it, that could entail a nucleotide here dropping out and being replaced by a more appropriate nucleotide. This is where the concept of electromagnetic profile really comes in handy. And I'm going to say here, I'm struggling to explain this. And I would probably benefit from having much better diagrams. But I believe that if you change A, you are changing its electromagnetic profile. That will then cause a change in electromagnetic profile in the catalyst. And the result of that might be that one nucleotide drops out and another one comes in. I'm getting annoyed. Because I feel like I'm failing to explain this properly. But it is my belief that chemicals can change their catalysts. If it's in the right circumstances, they can modify their catalysts. And the way, if we think about the shape of an RNA catalyst, it's all dependent on its A, T's, C's, and G's. And I think if you bully this enough, if chemicals A and B come to this catalyst and bully it enough, they can get one nucleotide to pop out and get another one to pop in. And if you don't like that explanation, just think about it in terms of electromagnetism. Because it might be that A has the modified version of the chemical A has a new electromagnetic profile, and that electromagnetic profile attracts one nucleotide and repulses another nucleotide. And that is enough to drive the idea that one nucleotide will drop out and be replaced by a different nucleotide. Anyway, the point being is that if you accept that chemical A and B can modify a catalyst to the point of changing its nucleotides, then they must also be able to do this to the DNA. They must also be able to do this to the DNA because, as we've seen, the DNA, this catalyst is also in the DNA, even if it's in disguise. This catalyst is embedded in the DNA. And so if A and B can bully the RNA catalyst into, changing shape, I think they can bully the DNA into changing shape. Or if A and B can bully the catalyst into swapping out one nucleotide for a different nucleotide, then ultimately they can do it to the DNA. My only regret in all of this is that I'm sort of slightly failing to make the convincing argument that A and B really can bully the nucleotide, bully the RNA catalyst into changing one nucleotide for a different nucleotide. But I'm absolutely certain it is true. I'm certain it is true because A and B have certain electromagnetic profiles. And if those electromagnetic profiles change slightly, then when they get to the RNA catalyst, they can sort of induce one nucleotide to drop out and induce another nucleotide to come in. I think that must be true. And the point is, if you accept that as being true, if you accept that the RNA catalyst can be bullied like this, then I think you can accept the DNA is bullied like this as well, even if it's to a lesser degree. So I'm getting sick and tired now. I regret that I didn't quite explain that as best as I could, but I'm going to have to live with that regret. So just to go back to this whole question, and by the way, I'm going to try and show you in a minute why this all relates to the ear. If I pull the ear, I change the DNA in the ear. I'm coming to that in a moment. So some of you might say, do catalysts really change the shape? Do the catalysts really change shape at the behest of the chemicals they bond in the way I've suggested, in this diagram here, this rubbish diagram? But the point is, there are certain things which modern biology accepts, because some modern biologists might say, no, chemicals cannot change the shape of their catalysts, full stop. But it is true that modern biologists accept that you can change, the proteins in your body. So, for example, if you do weight training, you modify the proteins in your body. If you do tanning, I believe, does that change the proteins? Well, it certainly changes. I think that must change the proteins as well. If you become tanned, that must be a change in proteins, I think. Don't quote me on that. Maybe that's wrong. But certainly if you get an earring put into your ear, then that is changing the proteins. So here's my point, right? Here's my fucking point. Oh, good God. When I pull on the earlobe like that, right? I'm definitely stretching proteins in my ears. So I'm stretching the proteins in my ears. When I pull on my earlobe, I'm stretching the proteins in my ears. And if we think about it, it must be that in certain cells, there are proteins and there are chemicals which are pushing towards those proteins and sort of squeezing them. And what would those chemicals be? Maybe the cell walls, but I think we can just say water. So when I pull my earlobe like that, I am pushing water molecules towards the proteins and they're squeezing the proteins. So to come back to everything I've said, we arrive at this situation where we have two chemicals. In this case, they're just water. We have chemicals, water molecules, coming to the protein and basically squeezing it, bullying it, changing its shape. So when I pull on my earlobe, we are in the situation of having chemicals coming to some of the proteins in my ear and squeezing them and bullying them. Now, the thing is that water is highly, is very easily polarized. So I say when you're squashing the proteins with water, when you're doing that, the water that gets very close to the proteins will adopt an electromagnetic profile which is opposite to that of the proteins. And the result of that is that these temporarily polarized water molecules will be attracted to the DNA. So and at least a few of them on some level will go to the DNA and try to equally bully the DNA into changing shape. So to repeat, when I pull my earlobe, what is happening, if we just pick a random cell in my ear, when I'm pulling on the earlobe, there will be a protein in one of the cells in my ear, and we are pushing water molecules towards it. We're pushing water molecules towards it. And because water is highly polarizable, these water molecules will take on an electromagnetic profile which is opposite to the protein. And because of that, these polarized water molecules, at least temporarily, will be attracted over to the DNA and will have some kind of interaction with the DNA. And they will bully the DNA in the same way they're bullying the protein. So anyway, I think that concludes that part of the talk. By the way, I'm just seeing some people raising points there. Someone says you're not changing the protein, you're changing something else. If you have any genuine questions, can you please leave them till the end, and I will come back and I will answer them. Oh, but anyway, I think I explained. I think that's that done. Let me just repeat that when you pull on your ear, if we just pick a random cell in your ear, there will be a random protein in that, or one protein where the water is moving, it's being pushed, it's being forced against that protein. Water is highly polarizable. It will temporarily take on the electromagnetic profile, which is opposite to the protein, which means as well as bullying the protein, it will simultaneously be bullying that part of the DNA which codes for the protein. And if you're saying, but the DNA is a long distance away, well, I can just say action at a distance. And if you're saying that's not going to change things on the nucleotide level in the DNA, that's not my claim. The claim is that on some level, the DNA is being changed. So that's that. But I want to repeat an argument which I think I've cocked up a bit or not properly described in this lecture, which is nevertheless a fundamentally important thing, is that I do believe you can bully a catalyst. You can bully an RNA catalyst, you can bully a protein catalyst, and you can also bully the DNA, and you can bully it into changing shape, and that will come about when if this is a bit of RNA and I say I want it like that, I want it like that. So if we have a bit of RNA like this and I bully it and say you must be that shape, then I think nucleotides will come along which will jump into the RNA whilst others jump out and thus hold the RNA in that position. I think if you bully the RNA into a certain shape, certain nucleotides within it will drop out and others will come in order to make that shape a permanent reality. I'm sure that must be true. And if you follow it through on the level of electromagnetic profile, you will convince yourself that it is true. If you really look at all the electromagnetic profiles involved, you will see that it makes sense that when you try to change the shape of the RNA catalyst, it will be possible that one nucleotide will be forced out and a more appropriate nucleotide will be drawn in. Look at it in terms of electromagnetic profiles, and I think it makes sense. And once you understand that is possible, that you can bully RNA catalysts, and likewise that you can bully proteins, you will see that you can also bully the DNA in the same way. So anyway, let's move on. So there's one third part that I want to present, but it's very short. And then there's some philosophical claptrap at the end. So let's just go back. Cell division. Cell division. So I want to briefly talk about cell division. Anyone who studied cells will know that they often or they always reproduce asexually, which means that you have a mother cell, an original mother cell, and at some point it divides into two, and you end up with two identical cells. One we call the mother cell, the other we call the daughter cell. So this is cell division. Why does it happen? Well, I think this is a very complicated question, and I'm not really going to go into it here. If you ask a chemist why a cell splits in two, I think they will give you an answer which will invoke what I call the surface area to volume problem. And what they will say is a cell is like a factory, and when it grows in size, the volume increases at a larger rate to the surface area. And this means that the cell, it means that the imports into the cell and the exports out of the cell can't keep up with the production rate of the cell, which causes all sorts of problems. So in the end, it splits into two. It's just, it's easier for the cell to split into two. It will be something like that. Now, personally, having looked into the surface area to volume problem, I think this is actually a fundamental law of physics, or we could call it a fundamental law of physics. It's a fundamental pattern that we see throughout the universe. And so that's something to mention. That's something to mention. I think the surface area to volume problem is like a key cornerstone which can explain many of the phenomenon that we see in the universe, not just at the cellular level, but also at the astrological level, etc. And also at the earthly level. But I don't want to talk about that today because that's way more complicated. What I want to talk about today is just that, okay, according to classical molecular biologists, when a single cell splits into two, it basically creates an identical copy of itself. However, there are some errors. So a molecular biologist will say a cell attempts to reproduce itself identically, and it almost does it. But it slightly falls short, and it isn't quite able to create a perfect copy of itself. In particular, when it tries to copy the DNA, it almost makes a perfect copy of its DNA, but there's a bit of a failure, and there are some errors. And so the DNA in the daughter cell is oh so slightly different from the DNA in the mother cell. Let me just have a glass of water before I cough myself to death. So that is what molecular biologists of today will say. They will say the cell reproduced itself, and it does so almost identically, and it wants to identically copy itself, and the DNA in the daughter cell is almost identical to the DNA in the mother cell, but it's not quite the same, and there are some errors. There are some errors which are made. However, I want to show you that my perspective is a bit different. And what I want to say is that there are no such things as errors. So let's suppose we have a cell and it decides, for whatever reason, it splits in half and becomes a mother cell and a daughter cell. In that case, how do we explain that according to my thesis? And why are the cells so identical? Well, the reason that the cells are so fucking similar is because they are occupying almost the identical region of space. So these two cells are right next to each other. And that they're literally on a pinhead together because cells are so unbelievably small that compared to the known universe, they literally do occupy the same space. I mean, they don't actually occupy the same space, right? So two cells, which are near each other, very near each other, don't actually occupy the same space. But to all intents and purposes, they kind of do because they're both on the same pinhead, because cells are absolutely bloody tiny. Cells are tiny. And so we can comfortably say that they are on the same pinhead. So the point is, these two, the mother cell and the daughter cell, essentially occupy the same point in space. And okay, what is the mother cell made of? It's made of protons and electrons. What is the daughter cell made of? It's made of protons and electrons. And what is the environment around them made of? It's made of protons and electrons. So the point is, it's from that premise, it's not difficult to understand that the daughter cell and the mother cell are going to be very, very, very similar. Because look, let's suppose I have a little bit of space. I have a little bit of empty space at the center of the universe. And I take some protons and electrons from my left pocket and I put them into that space, that empty space in the center of the universe. Then they will take on a certain configuration. Okay, then I'm going to remove them. And then let's suppose I take a second collection of protons and electrons from my other pocket, from my right pocket, and I put them in exactly the same empty space at the center of the universe. Guess what? They will take on a configuration which is exactly the same as what the other group of protons and electrons from my other pocket took on. Okay, so there is no surprise here that if these two cells occupy virtually the same point in space, that they will end up looking virtually identical because they're the mother cell is a collection of protons and electrons. The daughter cell is a collection of protons and electrons. So if we put them into the same space in the universe, those protons and electrons will rearrange themselves into the same pattern both times. Again, I feel like the point I'm making is unbelievably simple, and I fear that I'm waffling it. I'm making it more complex through my waffle. So it's not surprise that the two cells are virtually identical. Why are they different, however? Why are they ever so slightly different? Why are these cells ever so slightly different? Well, because they're not actually occupying the same part of the universe, are they? Because it's not possible for mother cell and daughter cell to occupy exactly the same space. And therefore, we should expect that there are a few little differences between mother and daughter cell. So, as far as I'm concerned, when the mother cell splits in two, so that we end up with a mother cell and a daughter cell, it's perfectly understandable that the two cells are very, very similar, but not quite identical. It's perfectly understandable that the DNA strands in the two cells are very, very similar, but not quite identical. But the interpretation of molecular biology is different. Because what molecular biology says, or their interpretation, is that when the mother cell splits into two, so that we end up with a mother cell and a daughter cell, it says that when the daughter cell's DNA is ever so slightly different from the DNA of the mother cell, it describes this as an error. It describes it as an error. So it says, oh, the mother cell has given birth to a daughter cell and it's almost identical, but there's a few bits of the DNA which aren't quite the same. So those are errors. That's unfortunate. Blah, blah, blah. To which I will say they're not errors. They're not errors, because how can that, if the laws of physics are governing everything, how can we say that those changes are errors? No, we have to accept that those changes are natural, and they come about because the daughter cell is occupying a slightly different region of space to the mother cell. But there is a little bit more to all of this. There is a little bit more to all of this. And what is that little bit more? Well, that little bit more is that there are very complex error correction mechanisms within the cell which mitigate the errors that arise in the DNA of the daughter cell. And you can see all of this described in James A. Shapiro's book, Evolution of You from the 21st Century, where he talks about these ridiculously complex error correction mechanisms, which mean that if the DNA in the daughter cell has, is not quite the same, is not quite identical to the DNA in the mother cell, then some of these errors at least are corrected and made correct. So how do we explain that according to our paradigm? Well, okay, so this is how I'd explain it. For us, the point is that there are no errors. So whatever the DNA, if we look to the daughter cell and we look at the DNA in the daughter cell, whatever that DNA is what it was meant to be. It was what it was meant to be all along, because the laws of physics are fixed and everything is predetermined. Now, I will say that when the daughter cell is produced, it is not in the position in space that it will finally end up in. So when the daughter cell is created, it starts off within the mother cell. It then leaves, it then separates from the mother cell, and it migrates to some small distance away from the mother cell. And because of this, it is changing its location in space. And so because it's changing its location in space, that means that the configuration of electrons and protons within it are going to be in a state of flux. How that manifests is that the DNA is kind of like in a state of flux as well, where it can't quite decide what it's going to be. So to repeat, the daughter cell begins life within the mother cell and comes out of the mother cell and migrates away a certain distance. And because of that, its environment is in a state of flux, and therefore the electrons and protons within it are also in a state of flux. And one manifestation of that is that the DNA is in a state of flux. And that means that the DNA, at its inception, the DNA in the daughter cell is not going to be quite the same as what it is by the end, when the daughter cell has fully broken away and taken up its new position. So the daughter cell must migrate from where it was incepted to where its final position is. And that involves a change in, its position, which means the protons and electrons within it are in a state of flux, reacting to its changing position, which has which manifests in the DNA being in a state of flux. Good fucking God. Oh. So if, let's just suppose, hypothetically, that at its inception, we could fix the daughter cell somehow or other into the position that it will finally occupy when all the process is over. If we could somehow magically do that, there would not be a flux in the DNA. The DNA would simply assume the final form that it will ultimately have. But it is the fact that the daughter cell is moving through space that means that its contents, and in particular its DNA, is in a state of flux and can't quite decide what it's doing. And that's why the DNA will change to some small extent. So the point is that the molecular biologists will say, oh, errors have been made and then they are corrected. To which we say, there aren't any errors. There aren't any errors, but if some of these errors are corrected, it's simply because the daughter cell is changing position in space, and as it changes position in space, that causes the DNA to change. To which you might say, how do you explain the error correction mechanisms that molecular biologists have observed? To which I will say this, because look, if you think about a beach ball, let's suppose we have a beach ball and it's on the sea near to the coast. So there's a beach ball floating on the surface of the sea near to the coast. The tide is coming in and out. The tide is coming in and out, and the beach ball moves in with the tide and out with the tide, in with the tide, out with the tide. Now, in that case, where the beach ball is floating on the water and moving in with the tide and out with the tide, no one would ever say, oh, the beach ball is causing the tide. Everyone would understand that it's the moon and the sun which are causing the tide, and the beach ball is just along for the ride. And so it's my belief, if we go back to the daughter cell and the DNA and the error correction mechanisms, it's my belief that the DNA is always destined to become what it becomes at the end of this process. So the DNA in the daughter cell is always destined to become what it becomes by the end of this process. There is, however, a state of flux, which I've just described, where it's a little bit unclear. And what I'm saying about the error correction apparatus is that it's just like the beach ball. It's just like the beach ball on the tide. It's just sort of, it's whatever the error correction mechanism amounts to, it's just machinery, which is sort of like the beach ball on the tide. It's sort of just being, it's not, what I'm saying is the error correction mechanism is not causing the DNA to change any more than the beach ball is causing the tide to come in and out. The error correction mechanism is just sort of, it's just on hand. It's just on hand as the DNA is changing into what it's always going to change into, as determined by the universe, as determined by the forces, the external forces, the external protons and electrons that are acting on the cell. So I'm saying the DNA, which, the final DNA which manifests in the daughter cell, that was always meant to be, and it was determined by the entire universe surrounding the cell. And if it looks like the error correction mechanism is actually manipulating the DNA into changing, I don't think that I don't think that must be true, even though I'm sure it looks like that. I'm sure it looks like that. But I think it must be more, even though it might not seem obvious, even though it might seem completely counterintuitive. I think the error correction mechanism is ultimately just in the same situation as the beach ball floating on the water. It's just it's just there for the ride. It's just being taken along. And the fact that the DNA is changing is because of the greater machinations of the universe surrounding the cell. That's my belief. Again, this is all sort of quite difficult to describe, and it's annoying me. Maybe diagrams would be helpful, but I'm not sure. I tell you what, though, there is one little thing if we look at my interpretation, there is one thing which I don't think does make sense. And that is, you see, according to molecular biologists, when the daughter DNA, when the DNA in the daughter cell is made, there are a certain percentage of errors. And by the time the daughter cell has fully formed, at least a percentage of those errors have been annulled, have been mitigated. So there's always more errors at the beginning, or more errors in the DNA at first, and then less errors by the end. But if what I am saying is true, we wouldn't expect that. If what I am saying is true, we would expect that there are a certain amount of errors in the DNA when the daughter cell is first conceived, and then there are a certain amount of errors in the DNA of the daughter cell by the end of the process, and in some cases at least, that would be more errors. So you'd have more errors in the daughter cell when it is finished than you had at inception, if what I am saying is true. So this is a problem. This is a problem with my thesis. Although I think I have an understanding of how to resolve it. I do think I have an understanding of how to resolve this, but I will say this is a problem. This is a problem because, to repeat, according to molecular biologists, when the daughter cell is conceived, there are a certain amount of errors in the DNA, but when it is finally formed, those errors have always been reduced. But in my thesis, when the daughter cell is conceived, there are a certain amount of errors in the DNA. And at the end, when the process is finished, there are a certain amount of errors in the DNA, and they could be more or less. They could be less, but they could also be more. There could be more errors in the DNA of the final finished daughter cell. And so I do recognize that I need to come up with a way of understanding why that is so. Although I kind of think I know why, and it's to do with the fact that the cell is better off. The daughter cell, when it's too near to the mother cell, it causes it to be more different than when it's finally when it's got a good distance away from the mother cell. It can kind of be similar, but I don't want to go into that here. I can see there might be some molecular biologists who say, Thomas, this is a load of rubbish. It's a load of rubbish. I've studied the error correction mechanisms. They're not just like a beach ball floating on a tide. And I can understand that. The one fact I will come back to where I think I'm correct, however, is that we can't talk about cells making mistakes. We can't say, oh, this cell divided and there were some errors in the DNA. No, I'm very sure that is not the correct way. Or look, that's a perfectly fine way of looking at things. But I think ultimately my interpretation of what is going on makes more sense from the perspective of physics. That there are no such thing as errors. That the cell divides because of some surface area to volume problem, and that the created daughter cell occupies virtually the same space in the universe as the mother cell, and therefore is very, very similar, but not the same, which means the DNA is very, very similar, but not the same. On that, I do think, I'm hitting a bullseye. Which is not just, look, I'm not saying that the biological interpretation is wrong. I'm just saying, ultimately, the physics interpretation, I think, is a good one. But I know there might be some people who've studied the error correction mechanisms in detail, and they think it's not just a beach ball floating on the sea. It's way more complicated than that. To which I will say, I'm not saying the error correction mechanism is just irrelevant, but I think I'm trying to get across the point that there are higher forces at work here, which are ultimately orchestrating events. Let me just. But I agree. One hole in my thesis is that if what I am saying is true, why is it so that at inception, the daughter cell has more errors in its DNA than by the time the process is over? Because if according to my thesis, there's not really anything that would explain that. And we might expect that at inception, the daughter cell has so many errors in its DNA. And then in certain cases, by the end of the process, the daughter cell has even more errors in the DNA. So I have to come up with a way of explaining that. Although I think I've got an inchoate idea in my head. Anyway, that concludes this TED Talk. I'm kind of a bit annoyed. I'm a bit annoyed because, as ever, I feel like I didn't really explain myself. It might have been more productive to have some better graphics, but you know what? I don't think so. I think that's only part of the problem. I think this stuff is just inherently difficult to explain. I think it is just inherently difficult to explain. What I want to do now is just come to a few loose ends, philosophical considerations, I've called it. You can put your pens down now. The lecture's over. Put your pens down and just, we're just going to have a little chat. To those of you who are in the chat, thank you for following thus far. If you would like to pose a question related to the talk, can you do so in about 10 minutes or so? And I will try and respond to what you've got to say. But please, just serious questions. I'm going to die here from a broken voice. Let's just quickly look over these philosophical considerations. I want to ask the question, were the biologists wrong? Because according to what I've said that that a lot of the stuff in the central dogma of biology contradicts the laws of physics. And I've said that the idea that there are random variations, which are central to the neo-Darwin paradigm, I've said that's also contradicting the laws of physics. So do the biologists, should the biologists be told off for this? Should they be given detention? I think the answer is no. Because look, just to be clear, I read Darwin's book on evolution when I was about 20 or something, 21, 22. The point is, I only worked all of this out when I was, basically 40. So for a good 20 years, I went along with the idea that random variations were possible and that the laws of physics were true. I held those two contrary ideas in my head all that time. So, it's taken me 20 fucking years to come to the conclusion that the neo-Darwin paradigm contradicts the laws of physics. It's taken me 20 years to work out that the central dogma contradicts the laws of physics. So I don't think, as much as people like Richard Dawkins are annoying, I don't really think the biologists, if it's taken me 20 years to work all of this out, I don't think I can be too harsh on the biologists. And in any case, it's understood that biologists are, they make biological observations. They're not physicists. It's kind of understood that the biologists are not physicists. So honestly, in the grand scheme of events, I think, it's easy to forgive the biologists for maybe getting this stuff wrong. I know I sound very smug saying all of this, and I know people will be looking at all of what I've said and picking holes in it left, right, and center. But I think the central idea of what I'm saying is correct. But I don't want to come over as smug. Oh my God. Oh, I don't want to come over as smug. So I won't. And I don't think it's to their discredit that maybe the biologists are contradicting the laws of physics. That said, however, who does deserve some detention? It's the physicists. The physicists, is that how you spell physicists? Physicists. Were the physicists wrong? The physicists have got it wrong. Kids, the physicists have got it wrong. They deserve detention. They're naughty boys. They need to be spanked on the backside. And I really want to say the physicists are wrong. Oh, I don't know whether I need to go and blow my nose, for God's sake. Oh. When footballers do that thing where they go and then I kind of need to go and do that because, for fuck's sake, I've been talking for too long. But anyway, the physicists were wrong, right? And I think the physicists deserve to have the cane taken to their backsides. And they deserve to have it taken to their backsides because these people are so bloody smug. Physicists, I'm sure it was back in the early parts of the 20th century. So we're talking about well over 100 years ago, or at least 100 years ago. Physicists were going on about, we've worked it all out. Physics is nearly done. Physics is nearly done. We've nearly worked it all out. We've nearly worked it all out. Well, here's the thing which really fucking annoys me, because physicists seem to think that if they're going to work out how the universe operates, all they have to do is explain the stars and explain the atoms. That's the mentality of these bloody physicists. They think if they can explain the stars and explain the atoms, they've explained everything in the universe. How about you explain all the other phenomenon in the universe, like everything that goes on planet Earth, apart from the stars and apart from the atoms? Do you know what I mean? This is how arrogant the physicists are. They spend all day studying all these like nuclear, quarks, and they've got like, red icicle quarks and gay ping pongs and all this kind of stuff. And you're like, they study all these tiny particles and they study space, but they don't ever study the fucking world. And it's like, a lot of these physicists don't seem to understand that if you want to come to the point where you say physics is finished, you're going to have to explain everything you see on planet Earth, including biology, including biological objects, including evolution, including sexual reproduction, but including everything. Like, why do men play football? Why do football matches take place? Why do people watch television? Why do they watch some television programs and think they're bad? Why? I don't know. Name me some phenomenon you'd like explaining, and it is the job of physics to explain it. If I prefer to have a pinch of lemon in my water rather than a pinch of orange, how do you physicists explain that? That's your job. You're meant to be explaining everything. And to come back to the point, when I'm looking at all this biological stuff and I'm asking the question, what's going on in the cell and why, or why are things going on in the cell, I should say, I'm looking, I call the physics department and I say, what forces are possibly behind what's going on in the cell? And they say, well, it's either gravity, electromagnetism, or the nuclear force and the nuclear force. And so I'm left to draw the conclusion, well, it must be electromagnetism. But the point is that all of this stuff which is happening in biology and the biological world, physicists have a duty to explain that. In the same way that biologists don't have a duty to get the physics right, because they're not physicists. But physicists claim to be able to explain everything. And if you're going to explain everything, you're going to have to explain all the phenomena on planet Earth. So I think the physicists do deserve a slap around the backside, because they're not interested in any of this stuff. They're not interested in explaining even the mechanics of a cell. Like, I would say that physicists maybe have personalities which make them averse to human beings and a lot of the things which go on in the world. Well, okay, fair enough. But can you at least get into what's going on in the cell, in the biological cell? Can you at least get into that world and try and explain that? But anyway, let me just say something here. I made a big deal about the electromagnetic paradigm. And I said that all objects have electromagnetic profiles. Molecules like DNA have an electromagnetic profile. And look, there's two problems to this. One is that some of you will just say, I don't buy this. For me, DNA is neutral. For me, RNA is neutral. For me, proteins are neutral. That's one problem. I personally think that the electromagnetic paradigm is kind of useful. And I think it can be made, we can understand things according to the electromagnetic paradigm. But that said, there are deeper problems with the electromagnetic paradigm. And let me just, mention 3 deep problems. Oh, let me just get a drink of water. One problem with the electromagnetic paradigm is that, on a micro level, we can understand positive attracted to negative. But what is the kind of universal perspective of all of this? I mean, what is the point? I mean, why do we never reach the problem? Why do we know, if positive is always attracted to negative, why do we never reach the point where, everything just becomes neutral? Like, what's the overall driver of all of this? That's one problem. A second problem is that I think if you think about covalent bonding, if you think about how energy shells, in when you look at atoms, they have certain very strange rules that they must follow when they do covalent bonding. Where you have two electrons in this shell and then 8 electrons in this shell, and so on and so on. It's more complicated even than that. I think those rules must surely be at odds with the electromagnetic paradigm, or it's like a second set of rules. What I'm thinking is, surely in some cases there might be a positive here and a negative here, and so we'd expect them to be attracted to each other. But because of this stupid kind of these rules about filling up shells with electrons, because of these rules about filling up shells with electrons, I think that might interfere with this electromagnetic paradigm, but don't quote me on that. I'm suddenly having doubts about that. But anyway, forget that. Here's the most stupid thing I find about the electromagnetic paradigm. The most stupid thing about the electromagnetic paradigm is that I don't know what charge is. I mean, and I really had to ask myself this question, which I'd never asked before, which is, what the hell do we mean when we say a proton is positively charged? What the hell do we mean when we say an electron is negatively charged? Because I really had to ask myself this question. And I couldn't find a good answer. You see, here's the thing. if you tell me that an atom has a certain size, I know what you mean. If you tell me that an atom has a certain mass, I know what you mean, I think. If you tell me that an atom has a certain shape, I know what you mean. If you tell me that an atom has a velocity, I know what you mean. If you tell me that an atom has a location, I know what you mean. But if you tell me that an atom has a positive charge or a negative charge, don't really know what you mean. Don't really, you're like, what the hell does charge mean in the final analysis? It doesn't mean anything. It doesn't mean anything. And by the way, this is one of the problems with science, I think, because what happens is that somebody in some distant point in the past, some great scientist, they study nature and they then contrive a scheme. They contrive a scheme which clarifies what they are seeing in nature. But then over time, that scheme is taught to school children and it starts to cloud their observation of reality. And I think that is true of the electromagnetic paradigm, because having been taught it at school, it's only at the age of 40 something when I asked myself the question, what the hell do we mean by charge? What are we talking about when we say electrons are negatively charged and protons are positively charged? I didn't even know what that means. The point is that whoever came up with this scheme was trying to give us a scheme by which to understand reality, rather than actually saying protons are positively charged. Like that's what I've thought. I thought protons are literally positively charged, but that's not really true. To say that a proton is positively charged, I think, is to say we're going to impose a scheme on things which helps us to understand everything. Do you see what I'm saying? Maybe I'm not explaining this well, but originally people didn't think that protons were positively charged and electrons were negatively charged. They just thought they were all neutral or something. And then, well, they didn't think they were anything. But then someone kind of came along and said, if we think that protons are positively charged and that electrons are negatively charged, everything makes sense, or so many things make sense. And so in the first instance, these ideas clarify. But eventually they cloud because when you're just taught this, rather than, thinking it up yourself, you then kind of genuinely believe on some level that protons are positively charged, electrons are negatively charged. Anyway, I think the electromagnetic paradigm can go a long, long way to explaining what's going on in the cell. But that said, I think it's got limits. And moreover, some of you might say, I don't buy into it anyway, because I think DNA is neutral. I think RNA is neutral, etc., etc. To which I say, we need a new paradigm. And we've opened up a Pandora's box. Because to repeat what I said at the beginning, if you do not like my explanations of why the DNA creates the RNA, creates the proteins, in terms of electromagnetics, that's fine. But for God's sake, can you come up with an alternative explanation? Because I want to know why these things happen. I want to know why these things happen. And so the onus will be on you to come up with, if you're going to detract from my ideas, please give me the alternative explanation. By the way, I've got an alternative explanation as well, which is stream theory, which I will present in a future fucking lecture. Anyway, let me just go through my notes to make sure I said everything. Let me just yes. Yeah, that's good. Let me just look through these. Yes. Okay, let me just mention this, because in all of this, I've said that According to the neo-Darwinian paradigm, they claim that random variations occur, random variations in the DNA. And I did ask myself the question, is it possible that quantum randomness might cause these random variations? Not that I think, that the people who came up with the neo-Darwinian paradigm were really thinking along the lines of quantum randomness, but I wanted to cover my bases. Now, what is quantum randomness? That's a can of worms. But if we suppose that it really does exist, could it affect the DNA? Actually, on some level, it could. It's not impossible. From what I understand from quantum randomness, it's not impossible that, in a blue moon, the DNA could be altered. But whatever, or at least that's my understanding. There might be some quantum physicists saying, "Shut the fuck up! You don't know what you're talking about." But I do think I've heard people say quantum randomness can change, cause a molecule to change. Maybe I'm talking horseshit. The bottom line is, if there are such things as, if quantum randomness is truly a thing, it's not causing the random variations in the DNA. Let me just, yes. Yeah. Let me just say one final thing, and then I will come to those of you in the chat who have got questions. And that is this, and this is another example of what I'm talking about, where someone introduces a scientific concept which clarifies things at first, but then later on it clouds things. And this, what is this to do with? It's to do with the idea that DNA is made up of a code which has the letters A, C, G, and T. This is something you will see talked about. People will say, "Oh, DNA, it's got this code, and it's got 4 letters A, G, C, and T, and this sort of, with these 4 letters, you can come up with all these different combinations, etc., etc." But one thing I want to say is that, and this goes back to what I was talking about, where you can have changes in the DNA which don't amount to nucleotides being changed. Because as I said before, if we take one of those letters, A, which stands for adenine, is it? So if we take A, which stands for adenine, it could be that in certain atoms in the adenine molecule, there are electrons which start, which jump up a level or jump up 2 levels or something. And what that means is that not all adenine molecules are the same. I mean, in general, if you take one molecule of adenine and another molecule of adenine, they're not the same. They're not the same because, are we really saying that the protons and electrons in one molecule of adenine are in exactly the same positions as the protons and electrons in another molecule of adenine? Maybe it's possible. It is possible, but it's not guaranteed. It's not necessarily going to be like that. And as I say, electrons can jump up and down, I think. So the point is, if you really wanted to get into it, maybe there's another alphabet we can form, because instead of just having A, there might be 10 different versions of the molecule adenine, which would lead to A1, A2, A3, A4, A5, all the way up to A10. And there might be 10 different versions of guanine. Or it might just be 2 different versions. There might be 2 different versions of guanine, 2 different versions of cytosine, 2 different versions of thymine, 2 different versions of adenine. But the point is that then, should we then talk about there being 8 letters in the alphabet or 40 letters in the alphabet? I hope the subtle point that I'm making is that it's nice to think that DNA is made up of these 4 letters, A, C, G, and T. That's a clarifier. It clarifies things, but it can also cloud. It can also cloud your mind eventually, because it clouds your mind to the fact that two adenine molecules could be different, and that the rearrangement of adenine of electrons and protons in one adenine molecule might be different from the arrangement of protons and electrons in another adenine molecule, even if that rearrangement is only quite subtle. And that goes back to what I've been saying, which is that, you know, there can be subtle changes in the DNA, which are, you know, which don't amount to nucleotides changing, don't amount to epigenetics changing, but they do still amount to changes. But anyway, I've blathered on enough. I feel as ever that I haven't given a full, you know, I haven't given a complete, I feel annoyed that I haven't quite explained everything properly. But nevertheless, there comes a point where you need to shut the fuck up. So that point's come now. Let me thank everyone who's listened. Thank you very much. Because if you weren't there, I wouldn't know if the sound wasn't working, and I could have just wasted my time. So if any of you have any serious questions to ask, I mean, listen, for those, you know, because I anticipate there might be some academics or intellectuals who come and watch this video. You know, my audience, you know, they're funny people. So if I open up questions to them, they may not ask serious questions, and they, you know, they might ask rude questions. So I don't want to indulge them too much because, like I say, very important academics, very important professional people will be coming to study this video, or maybe not. And I don't want to put them off. But anyway, if anyone has a question, please ask it now or forever hold your peace. Let me just see if I can scroll up. In any case, thank you to everyone who's listened. I really appreciate you coming in and listening, simply because it allows me to know that the audio is working. I didn't want to get, because I did just want to do the stream privately originally, and then I was going to publish it afterwards. But the problem with doing it that way is you then worry that things are going wrong during the stream, that the audio is not working. And if you're doing a 3-hour stream and you get to the end and you realize the audio wasn't working, you've wasted your time, and you know it's really annoying. So if there are any questions, guys, I'll give you 30 seconds more to ask them. Other than that, we're going to wrap up immediately. General Red Herring says, the central dogma of biology was disproven long ago since the discovery of reverse transcriptase, an enzyme that constructs DNA from RNA. I was going to say indeed, as if I know what you're talking about, whereas at this point, I've only got a vague recollection of what you're talking about, but you're right. I'm sure you're right, but I'm sure you're right, General Red Herring, and I'm sure reverse transcriptase. I'm sure this is one of the many things that I came across when I was studying molecular biology of the cell. So that's a very good point, General Red Herring. But just to repeat, I'm not balmy for saying that lots of people still believe the central dogma is true. You know, it's one of those things, and we've seen this in the political arena as well, where the truth is out there, and a lot of people know the truth, and yet still the false idea prevails amongst certain people. So thank you, General Red Herring, for that. Managerialite Toaster 3456 says, if viruses have never been isolated and observed, how do you know that RNA or DNA exist? And how will you observe this process in order to test it? Well, look, managerial tester, I'm just taking, ultimately, I'm believing what the molecular biologists are telling me. Although I will say, look, if viruses have not been isolated and observed, does that mean that RNA and DNA have not been observed? But you know what, managerial toaster, I'm not, I don't know, we've discovered in recent years that we've been lied to about so many things. So I'm not here to doubt what you're saying. All I'm saying is that I have implicitly trusted what the molecular biologists have told me, and from that I've come up with a thesis. If it turns out that the molecular biologists were not conveying the truth, then I'm up shit creek without a paddle. But this is the world we're living in. We're living in a world where a lot of the knowledge that we've been taught turned out to be false. So let me just said, CCG says, Thomas, couldn't you go back to interviewing Faust, Horace, Stephen J. James et al.? They were such fun. I'm not interested, CCG. I've moved on. I've moved on. General Red Herring says, moreover, they, and I think he's referring to proteins, are responsible for epigenetic changes, such as deactivating certain genomic regions through chromatin coiling. Similarly, proteins are used for gene editing, hence altering DNA. Yes. So I don't dispute any of that, General Red Herring. I don't dispute any of that. And all of this stuff that you're talking about was what's the word? It was all important to me when I was studying molecular biology of the cell back in 2019. And General Red Herring continues, he says, besides, technically DNA is acted on by proteins all the time, from shuttling to lysis. Indeed. And this goes back to what I was saying in my lecture, if I can pompously call it that, which is that it's just ridiculous to think that the DNA is somehow immune from the rest of the cell, that it's somehow locked away in a vacuum of space, shut off from everything else. Okay, General Red Herring says, regardless, the central dogma does not insinuate that proteins do not affect proteins. Instead, it postulates that you cannot use proteins as templates to create mRNA or DNA in a similar manner to how DNA is used as a template for mRNA during transcription and mRNA for proteins. My brain's gone after 2 hours. Let me just read that again. It postulates you cannot use proteins as templates to create mRNA or DNA in a similar manner to how DNA is used as a template for mRNA during transcription and mRNA for proteins. Well, yes. Yeah. No, yeah. And I'm not claiming that you can use protein as a template to make DNA. Yeah, I'm not saying that the proteins can make DNA, but I'm saying if you change the proteins, you can change the DNA, but you wouldn't be making a new copy of the DNA. I think this point comes back to what I was saying at the beginning, which is that for me, I don't really see that during the in the activity of the cell, I don't see proteins as being created. I don't see mRNA as being created. It's always there, because all I see is protons and electrons being reconfigured. So I know that people will say DNA creates proteins, or DNA creates RNA, which creates proteins, but proteins do not create RNA, which creates DNA. Just to be clear, I'm not talking about creativity, but I'm talking about effects. I'm saying the DNA Because for me to repeat, RNA already exists in the cell. The proteins already exist in the cell or in the environment as well, but they exist in the universe. And what the DNA does is the DNA changes configuration, and that causes a reconfiguration in the RNA, which causes a reconfiguration of the proteins, and the reverse is absolutely true. But this is true. I'm not saying that proteins can create DNA in the same way that DNA can create proteins. Just to be clear. Imam Pudama says, do you think cells can purposely direct evolution by modifying DNA through the mechanisms you've been talking about? Well, yes and no. I don't think there's any purpose, because I think a cell is just a collection of protons and electrons. So I don't think they can purposely direct evolution. But I think that when evolution happens, I think if the environment changes, that can cause a change in the DNA. So the DNA can be modified directly by the environment. That's what I believe, because everything's protons and electrons. So even if the environment can only mildly modify the DNA, it's still modifying the DNA. And that, yes, Emmanuel, I totally believe in what some people call directed evolution, whereby the environment causes changes in the DNA. I totally believe in this. The only thing I would say is I don't believe that the cell is acting with purpose. I don't think the cell is acting with purpose. Now, in his book, Evolution, A View from the 21st Century, James A. Shapiro talks about the work of the Nobel Prize winner from 1981. What was she called? I don't remember her name. She won the Nobel Prize for biology, I think, in 1981. And what she saw was that in response to stress, if you put certain plant genomes or certain plant cells under stress, the genomes would rearrange themselves. So that there was, the DNA, there were sections of the DNA which would change positions with the others. I think that's more or less what the idea was, that if you inflicted stress on these plants, then the plants, the DNA or the genome, it kind of rearranged itself. Now, I wouldn't say that the plant was purposely doing this. I wouldn't say, oh, the plant is purposely doing this. What I would say is that everything's made up of protons and electrons. So the environment, which is made up of protons and electrons, is going to cause changes in the cell. And it's not just going to cause changes in the cell, it's going to cause changes in the genome, because the genome is not some special thing which lies outside the laws of physics. So the fact that the genome of the plant rearranged itself was just a simple consequence of the environment changing. The problem is that biologists have mystified everything by giving DNA this special status which can't be touched, and that's really silly, because it's all kind of it's kind of obvious. If I throw a ball over my neighbor's fence, it might smash through his window. And similarly, if you change the environment of a plant cell, that's going to have knock-on effect in the interior of the plant cell, which will have a knock-on effect on the DNA. It's really not it's not rocket science. So thank you for that question, Iman. General Red Herring says humans and animals in general do not have cell walls. Yeah, because earlier on I was talking about pulling on the earlobe, and I said, maybe the cell wall of one of the cells in my ear will end up squashing against a protein. And of course, human cells don't have cell walls, but you know what I meant? I meant the cell membrane. So, you know, I did mean the cell membrane there, General Red Herring. Anyway, CCG says, are you watching the World Cup with your dad? Well, I should be, but I'm honestly not. It's passing me by at the moment because I've got a lot on, and the World Cup is on at a very bad time. It really is, which has put me off it big time. Okay, listen, I think I'm going to wrap up very soon because I have to get off to have my hair cut. I've got an appointment at 5:30. Iman Paduama says, I don't see any comparison between the way they inferred the existence of DNA and the flaky way they infer the existence of viruses. Imam, I don't know. I mean, look, I believe in atoms. And one thing I've been asking myself in the last 5 years is, how do they know atoms exist? And can they see them under the microscope? And well, it's as you say, a lot of these things have been inferred rather than actually seen. But then again, what does it mean to actually see something? Because I'm sure that when we see things, we're really inferring that they're there. So I don't, it's a can of worms, Iman. That's all I'm going to say. CCCG says, my favorite part of Diary of a Toilet Goer was when you were shitting at work and someone turned the lights off when you were on the bog. Hilarious. Well, thanks, CCG. Thank you very much. I appreciate the compliment. That, you know, I'd like to think that Diary of a Toilet Goer was my magnum opus. So, you know, it's not really appreciated by the masses. You've got to be, you know, very, very highly intelligent to understand all the clever literary, you know, the clever literary stuff that's going on in the Diary of a Toilet Goer. So thanks, CCG. Glad you liked it. It's a compliment to yourself that you're so highbrow that you could read it. All right, listen, I'm going to have to wrap up. I've made the mistake of looking at too many questions. Iman Puduema says, do you know about Michael Levin's research? He's proven that morphogenesis is not in DNA, but is in nested programs within the body's bioelectric field. Cells intelligently follow them. I don't know who Michael Levin is. Well, it vaguely rings a bell, but I don't think I know who it is, Iman. I was somewhat up to date when I was looking at everything in 2019 and 2020. I've since just kind of gone off on a tangent. I mean, this is one of the things about doing scientific research is that you don't have time to look at everyone else's. This is so far from being true, because ideally you'd want to know what every single person ever in the entire known universe had said about this subject. And in reality, you just make do by looking at a few different sources, and then you say, oh, I'm going to drown in this if I don't move on. And your own ideas overtake you. And so that is that. It's not in any way a satisfactory story. CCG, I don't have any plans to make audiobooks of my novels now. I've given up on trying to sell novels. General Red Herring says, I'm not technically trying to disprove the central dogma. You're tackling something else. Maybe that's a fair point, because to repeat, I'm not saying that proteins can make DNA, but I'm saying that proteins can affect DNA. So I take your point, General Red Herring, which again comes back to the idea that the central dogma is badly worded, or it's not clear what it means. But anyway. CCG is asking this question. How do you think this theory applies to the false corral snake that mimics the real venomous one, but whose bands only go around the top part of its body? Well, there's a lot I could say about this, but I don't think we really have time to go into it. And in some ways, this is a very interesting question about there's certain animals. They look similar to other animals who are poisonous. And what this means is that, you know, another animal, if it sees this fake poisonous animal, will say, oh my God, I better run away from it because it's poisonous, even though it's not poisonous. It just looks like a poisonous animal. So how do I explain this? I don't know that I can say anything worth saying in a small amount of time. I asked this question, by the way. You can ask this question that, you know, why do wasps look like bees? Well, I suppose wasps have got a bit of a sting. Bees can potentially lethally sting you. Wasps don't, you know, they hurt, but it doesn't really matter. Is there anything I can say in 2 minutes about animal mimicry? I don't know, but if two objects look the same, then they might be quite similar. So, you know what, CCG, I'm going to duck out of that question. I can't say anything meaningful. I can't remember all the conclusions I came to about animal mimicry. I can't remember them. I did all that work in 2021, and I've forgotten at this stage. And I don't think I've got anything insightful to say in 2 minutes. But nevertheless, that's a very interesting question in biology about this, you know, one animal mimicking another animal who happens to be poisonous. And the whole resolution of why that works has been playing on my mind. I'm sure I did resolve this in some way, but maybe I didn't. I'll have to leave that. Okay. You're welcome, Managerial Toaster. Okay, you're welcome, chat. Okay. I'm going to leave it there and wrap up because I better rush off to the hairdressers. So sorry I couldn't answer that question about animal mimicry better. But yeah, I can't say anything interesting. I can't remember what conclusions I came to. And maybe I didn't come to any insightful conclusions on that particular topic, but it was certainly a topic that very much interests me, and I want to get to the bottom of it and explain it using stream theory. Thank you very much to everyone who tuned in. I really appreciate it because it allows me to know that there are not any technical problems and there are not any sound issues. So thanks to everyone listening in. I suppose some of you are paid agents and you're forced to listen to my work. So this maybe wasn't the most interesting thing for you. But anyway, thanks very much for listening in, kids. Take care. Have a great day. Enjoy the World Cup. And thank you very much for listening to my TED Talk. All right. Cheers.